On July 24th, 2026, SpaceX rolled its biggest rocket ever built out to the pad in South Texas for the 13th full test flight of Starship, and almost nobody inside the company was treating the number lightly. After the string of problems that had plagued earlier flights that year, this mission needed to go right. What actually happened over the following hour turned into one of the most consequential test flights in the entire Starship program, mixing a genuine breakthrough with a fresh reminder of just how unforgiving rocketry still is, even for a company that's landed boosters hundreds of times before. To understand why this flight mattered so much, you have to rewind slightly to what came before it. Flight 13 was only the second outing for the newest version of Starship, known internally as Version 3, or Block 3, a substantially redesigned vehicle built to eventually carry far more payload and fly far more reliably than the earlier Starship generations. The first flight of this new Block 3 rocket, back in May, had been rocky. The booster missed its intended splashdown target, and the ship suffered an engine shutdown early into its ascent, cutting the mission's usefulness well short of what SpaceX had hoped to demonstrate. So Flight 13 wasn't just another routine test hop. It was the first real chance to show whether the redesigned Block 3 hardware could actually deliver on its promises. Getting the rocket off the ground at all turned out to be its own ordeal. SpaceX's first attempt to launch Flight 13 came on July 16th, and it ended before the rocket ever left the pad. As the Super Heavy booster's 33 Raptor engines began their ignition sequence, the flight computer detected a problem and automatically halted the countdown at the last possible instant, protecting both the vehicle and the launch tower from potential damage. Investigators quickly traced the issue back to a handful of the booster's oxidizer turbopumps. Moisture had apparently built up inside some of the pump hardware, and when that moisture came into contact with the deep cold of the cryogenic propellant, it froze solid, throwing off the normal spin-up behavior of the turbopumps in at least 4 to 6 engines. Rather than risk pushing forward with faulty hardware, the automated abort system did exactly what it was designed to do and shut the whole attempt down at T0. SpaceX spent the following days swapping out the affected engines. In an interesting bit of due diligence, one of the removed Raptor engines was shipped off to the company's test facility in McGregor, Texas, and put through a full-duration burn on a static test stand to confirm the fix had actually solved the underlying problem before anyone trusted new hardware back on the vehicle. With replacement engines installed, SpaceX moved toward a second launch attempt on July 23rd, only to scrub that one too, this time simply because the weather over Starbase refused to cooperate. Finally, on July 24th, with clear skies overhead, Starship got its shot. After a brief hold built into the countdown clock, the vehicle lifted off cleanly, and this time, all 33 Raptor engines on the Super Heavy booster fired exactly as intended, a genuinely difficult engineering feat, given how many individual engines have to ignite, throttle, and stay synchronized simultaneously on a vehicle of this scale. Standing roughly 4 to 8 feet tall, taller than a 40-story building, the fully stacked Starship thundered off the pad and climbed into a mostly clear Texas sky. The ascent followed the now familiar hot staging profile SpaceX has used on recent flights, where the ship's engines ignite while it's still attached to the booster, using their own thrust to help physically push the two stages apart, rather than relying on a slower, more traditional separation sequence. The separation went smoothly. The Super Heavy booster then flipped around and fired a subset of its engines in what's called a boost backburn, a maneuver designed to cancel out its forward momentum and steer it back toward a controlled descent, while the ship's own 6 engines lit up to continue carrying it onward toward space. This is where the flight split cleanly into a story of 2 very different outcomes for the booster and the ship. Start with the booster, because that's where the flight ran into real trouble. Super Heavy descended back down toward the Gulf of Mexico for what was always planned as a controlled, but ultimately disposable, splashdown rather than a return to the launch site. As it approached the water, the booster attempted to relight 13 of its engines to slow itself down for landing. Only 10 of those engines actually reignited, and 5 of those 10 failed again just seconds later, leaving the booster with noticeably less braking thrust than planned as it neared the surface. The result was a harder-than-intended splashdown, with the booster hitting the water going faster than SpaceX had hoped. Even so, the splashdown was still broadly controlled, and because SpaceX always intended to lose this particular booster in the ocean rather than attempt any kind of recovery, the harder impact didn't turn the moment into a failure so much as a data point. One more example of the kind of high-stakes engine relight problem that SpaceX still needs to iron out before booster performance becomes fully consistent. The ship, on the other hand, had close to a flawless run. Once in space on its intentionally suborbital trajectory, Starship's upper stage carried out one of the more ambitious payload tests attempted on any Starship flight to date. Tucked inside was a batch of 20 next-generation Starlink V3 satellites. And rather than simply carrying dummy mass simulators the way earlier test flights had done 6 times in a row, this time the satellites were real, functional hardware. Once deployed, they unfurled their solar panels and antennas and briefly attempted to link up with SpaceX's existing Starlink constellation using laser communication links between satellites, testing real operational capability, rather than just proving the deployment mechanism worked. Because the flight path was intentionally suborbital, none of these satellites were meant to stay in space. They came back down and burned up in the atmosphere roughly 20 minutes after being released. 6 of those 20 satellites carried something extra. Specialized camera rigs bolted on, specifically to photograph Starship itself as they drifted away from it. The idea was to capture detailed imagery of the ship's heat shield and engine section from multiple angles in space. A maneuver SpaceX compared to the rendezvous pitch maneuver NASA once used on the space shuttle, where the shuttle would flip over in orbit, so the space station crew could photograph its heat shield tiles for damage before it came home. Having satellites document Starship's condition in real time from just after deployment gave engineers a fresh source of external close-up data on how the vehicle's heat shield was holding up in the vacuum of space, days and flights before that heat shield would actually get tested by the extreme heat of reentry. Starship's ship also carried out an in-space engine relight, successfully reigniting one of its Raptor engines while coasting through space, another incremental but important milestone. Since predictable in-space relights are essential for any future mission that needs to adjust its trajectory, deorbit itself precisely, or eventually attempt orbital refueling and repositioning. Then came the part of the flight that genuinely surprised people watching, including some inside SpaceX. As the ship curved back down through the atmosphere toward its target splashdown zone in the Indian Ocean near Western Australia, it survived re-entry heating and executed the landing flip maneuver Starship performs in its final seconds, rotating from a horizontal belly-first orientation into a vertical position just before touchdown. It then splashed down in the ocean, and rather than tipping over and breaking apart on impact the way earlier test ships had after similar water landings, this Starship touched down softer than any previous Starship splashdown on record. SpaceX's own commentary team called it the gentlest ocean landing the vehicle had ever achieved. The ship did eventually tip over onto its side in the water, something engineers had anticipated given the vehicle wasn't designed to float upright indefinitely, but crucially, it stayed structurally intact. It didn't explode or break apart the way several previous Starship prototypes had during earlier re-entry and landing attempts. Instead, it settled belly up in the ocean, fully intact, and kept transmitting telemetry data back to mission control even after landing. SpaceX quickly confirmed on their live broadcast that the ship was floating and still sending data, a first for the program, since no earlier Starship had survived an ocean splashdown well enough afterward to keep operating and communicating from the water. That survival gave engineers an opportunity nobody had ever really had before with this vehicle, the chance to actually go inspect a splashdown Starship up close while it was still in one piece. SpaceX sent a drone out to the floating vehicle, capturing detailed footage of the ship bobbing in the waves, including views of a small fire that had broken out near its nose section sometime during or after splashdown. Despite that fire, the ship remained afloat and largely intact for the inspection, giving SpaceX real, physical footage of exactly what the vehicle's heat shield and structure looked like immediately after a full flight, rather than relying purely on sensor data and telemetry the way they'd had to on almost every previous test. Elon Musk later indicated that SpaceX intends to actually recover this particular Starship from the ocean, rather than simply letting it sink, which, if it happens, would give engineers an unprecedented opportunity to physically examine a flown ship's heat shield tiles, structure, and engines back on land, rather than through remote inspection alone. Taken together, SpaceX summarized Flight 13 as a successful full end-to-end test of the ship, covering everything from stage separation all the way through final splashdown, and said it completed the verification steps needed before attempting an actual orbital Starship flight in the future. The booster's rougher, landing was treated as a known issue to fix rather than a fundamental setback, especially since SpaceX had never planned to reuse this specific booster anyway. The stakes for what comes next are considerable. Not long after Flight 13, Musk announced that Flight 14 is expected to push further than any Starship mission before it, with SpaceX planning to attempt catching the vehicle using the giant mechanical arms on its launch tower, nicknamed Mechazilla, a feat that has previously only been performed with the Super Heavy booster and never with the ship itself. Catching the ship this way would require Starship to actually reach orbit first, rather than the intentionally suborbital hops the vehicle has flown so far, marking a significant jump in ambition for the program. SpaceX's president, Gwynne Shotwell, had said even before Flight 13 launched that if this mission went well, the company hoped to attempt its first fully orbital Starship flight on Flight 14, to be followed by Flight 15, which would mark the first ever Starship launch from a pad in Florida rather than Texas, opening up a second launch site for the program entirely. It's worth stepping back to appreciate just how unusual this entire approach to rocket development still is. Most rockets throughout history have been designed on paper, simulated extensively, and only flown once engineers were reasonably confident the vehicle would work as intended, with failures treated as rare, expensive setbacks. SpaceX has built Starship almost the opposite way, flying real, full-scale prototypes over and over, deliberately pushing them until something breaks, then rebuilding and flying again within months rather than years. It's an approach that looked chaotic from the outside during Starship's earliest flights, several of which ended in dramatic explosions visible for miles around Starbase, but it's the same iterative philosophy that let SpaceX perfect the much smaller Falcon 9 booster landing years ago, turning something that seemed almost impossible into a routine, repeated operation. Flight 13 is another data point in that same long, expensive, occasionally explosive process, except this time the balance tipped further toward success than failure, especially on the ship side of the mission. The Starlink deployment portion of Flight 13 deserves particular attention because it points toward the actual business case driving much of Starship's development in the first place. SpaceX's existing Falcon 9 rocket already launches the vast majority of Starlink satellites currently in orbit, but Starship is designed to carry vastly more mass and volume per launch, meaning a single Starship flight could eventually deploy far more satellites than several Falcon 9 missions combined. Successfully releasing 20 functional next-generation Starlink V3 satellites on Flight 13 and having them attempt real laser communication links with the existing constellation was a meaningful signal that Starship is inching closer to becoming a working satellite delivery vehicle rather than purely an experimental test article. The satellite's brief but real operational role, even on an intentionally suborbital flight destined to burn up minutes later, distinguishes Flight 13 from the 6 previous missions that only carried inert mass simulators shaped and weighted like satellites, but incapable of actually doing anything once released. The booster's rougher splashdown, meanwhile, fits into a pattern SpaceX has wrestled with since introducing this newest Block 3 hardware. The same category of problem, engines failing to relight reliably during critical landing burns, had already surfaced in slightly different form back on the Block 3 debut flight in May, when the booster missed its splashdown target entirely. Seeing a related issue resurface on Flight 13, even in a more contained and less damaging way, suggests SpaceX is still working through growing pains specific to this redesigned version of the booster's engine and propellant systems, separate from the issues that plagued the very first generations of Starship years earlier. The company's engineers will now dig through the flight data to figure out exactly why 5 of the 10 relit engines cut out again so quickly, in much the same way they traced the earlier launch pad abort back to frozen moisture inside the oxidizer turbopumps. So, what does Flight 13 actually add up to? A booster that came back to Earth in a controlled but rougher than planned splashdown after several of its engines failed to relight properly during the final landing burn, underscoring that SpaceX still has real engineering work ahead of it on booster reliability. But paired with that, a ship that performed close to flawlessly, successfully deploying real operational satellites for the first time, executing an in-space engine relight, surviving reentry, and then pulling off the softest, most intact ocean splashdown any Starship has ever managed, intact enough that SpaceX could send a drone out to inspect it afterward, and is now planning to physically recover it. For a program that has spent years working through spectacular explosions and dramatic mid-flight failures on live television, an ocean landing calm enough to leave the vehicle floating, transmitting, and recoverable represents a genuinely significant shift. Exactly the kind of steady, unglamorous progress that eventually turns an experimental rocket into an operational one. With Flight 14 now aiming for actual orbit and an attempt to catch the ship itself out of the sky, SpaceX has set the bar for its next test even higher than the one Flight 13 just cleared.